All right, welcome to the video for 4A method students. In this section we're going to look at quadratic functions and we start off with solving quadratic equations. So big part of the methods course. Once again, building on things that you've done before. A lot to remember here, so let's get stuck into it. If we're asked to factorise any sort of polynomial, and obviously we're focusing on quadratics here, then we typically will look to, as a default, factorise and then apply the null factor law if we can. So with quadratics, often what we're going to look for first is just a highest common factor. I would tend to say when you're solving or factorising, try the easiest methods first, and then if that doesn't work, try the next easiest method. So you don't go straight to the hard ones, you try the easy ones first. So look for a common factor. See if we can factorise by inspection, just by getting the expression into two brackets. Some of you I know use the cross method and that's fine. There is also the difference of two squares or perfect squares that you might recognise when we're trying to factorise. If those things don't work, that's when you might go to the sort of harder ones of completing the square or using the quadratic formula. Using the quadratic formula will always work if there is a solution, but it is not going to be the fastest way to solve an equation. So just be mindful to try the easy methods first. All right, so let's get stuck into a few different ones. Example 12, we're being asked to solve a few equations for x. First equation is 3x squared, take away 75 equals 0. I always believe if you can only see x once in an equation, then solve by using inverse operations. Just get everything else to the other side. So we can do that one by adding 75 to both sides to get 3x squared equals 75. You can then divide both sides by 3 to get x squared equals 25. And of course the inverse operation for squaring is taking the square root. So x will equal the positive or negative square root of 25, which is plus or minus 5. Okay, so two different solutions there, x equals positive and negative 5. And remember that quadratic equations can have two solutions, or one, or sometimes none. Second one, we've got a quadratic trinomial, so we've got an x squared and we've got an x, which means we can't just use inverse operations like the previous one, but what we can do is try to factorise. So look for a common factor. Unfortunately there isn't one, but what we can do is try to get this into two brackets. If you can do it by inspection or by trial and error, that's fine. If you've got other methods like your cross method, then go for it. I would just think of this as we need two numbers that multiply to negative 36 but add up to 9. So at factors of 36, we can try things like 2 and 18, 3 and 12, 6 and 6. If we need them to add to positive 9, then 12 and 3 or 3 and 12 looks like the winning pair. We need positive 9, needs to add to positive 9, so we need a plus 12 and a minus 3. And of course that product needed to equal negative 36, and it does. So we've done the factorising, and now via the null factor law we can say x plus 12 equals 0, or x take 3 equals 0, which means x will equal negative 12, or x will equal positive 3. Okay, last one, for example 12, this one's got x squared equals 6x minus 3. Now for most of our methods we want to have equals 0 on the right hand side, so let's fix that up first. Take away 6x from both sides, add 3 to both sides. If we do try to factorise, and it's good to look for that first, we're pretty quickly going to realise that our only real factors of 3 that we can use that are whole numbers at least are going to be 1 and 3, and there's no way I can make 1 and 3 add up to negative 6. So factorising, not going to work. What we can try then is either completing the square or using the quadratic formula. Now, if you do choose to complete the square, you need to make sure that x squared is just 1x squared, not 2 or 3x squared, doesn't have another coefficient in front of it. And completing the square can get a little bit messy if the coefficient of x is an odd number. So for that reason, I tend to favour the quadratic formula, but it does depend on the question and it does depend on what you feel more confident with. Let's do this one. Actually, let's do this one with completing the square because it'll work nicely, but we can quickly show quadratic formula as well. So if we're going to complete the square, complete square, x squared, take away 6x, and what we do is we add half of the x coefficient squared, and then take away half of the x coefficient squared. We still have plus 3 and we still have equals 0. So that gives us x squared take away 6x. This is going to become, well, technically negative 3 squared, but negative 3 when you square it gives you 9, so we're going to get plus 9 here, then minus 9 and plus 3. And the idea with completing the square is that once you've done this, your first 3 terms should now factorise into a perfect square. And they do, because when we think of multiplying to positive 9, oh, hang on, done the wrong thing there. That shouldn't be a plus. We need the two numbers in the brackets to multiply to positive 9 and add to negative 6. And x minus 3 times x minus 3 will give us that. We also have minus 9 and plus 3, so that becomes minus 6 equals 0. So now what you notice after you've completed the square is that x only appears once. So you can now solve this by inverse operations. You get x minus 3 squared equals positive 6. If we shift this up here, we'll then get, we can take the square root of both sides to get x minus 3 equals plus or minus the square root of 6. So x will equal plus or minus the square root of 6 plus 3. So completing the square works nicely enough for that one. If we, let's give it a go. I'm going to need more space, so I'll flick over to the back of this page. The equation was x squared minus 6x. What did we do? It was plus 3, wasn't it? Yep, plus 3 equals 0. So for the fans of the quadratic formula, this is how it would look if we solved using the quadratic formula. X will equal negative b, so negative 6, plus or minus the square root of b squared minus 4 times a times c, all divided by 2a, which is 2 times 1 in this case. And what I probably should have done at the start is just written down a equals 1, b equals negative 6, and c equals 3. So we're using those values in the quadratic formula. And then we just try to simplify that and work it through. Well, that becomes a positive 6 plus or minus the square root of 36 minus 4 times 1 times 3, so minus 12 all over 2. X equals 6 plus or minus the square root of 24 over 2. And then we can go a little bit further with the square root of 24. Remember that 24 is equal to 4 times 6. So that will become the square root of 4 times 6. It's all over 2. Whoop. Recess time. So x equals 6 plus or minus 2 root 6 on 2, and then you'll notice we've got a common factor of 2 on the top, divided by 2 on the bottom, so we can actually divide everything by 2 to get x equals 3 plus or minus the square root of 6, which is what we got when we completed the square as well. All right, also in this section is sketching parabolas. There's a bit in this actually, 4a. We're pretty much revising the entire quadratics topic. So when we're sketching parabolas, can depend a little bit on how the information is given to us as to what method we're going to use. Typically, if the equation's in turning point form, then we'll use that to identify where the turning point sits. Just remember that in turning point form, you've got a dilation factor in front, which is a. The value of h is going to move your graph left and right. K is going to move your graph up and down. And of course, if a is negative, you'll get a reflected parabola. So that typically is the easiest way to sketch a parabola if it is in turning point form. And we can complete the square to get the graph into turning point form if we need to. A couple of other things or techniques we might use depending on how the information's given to us. If it's in polynomial form, so if everything's sort of expanded out, we can use this idea that the x-coordinate of the turning point is negative b over 2a. But another option would be to complete the square to get that graph into turning point form. If it's given to us in factorised form, well then what this is nice or useful for is that we can work out the x-intercepts straight away. The x-intercepts will come from each bracket equaling 0. And then if you do know the two x-intercepts, you know that the x-coordinate of the turning point will actually be halfway between the two x-intercepts. So let's give it a go with some examples. So in example 13, we've got to sketch the graphs of the following parabolas, labelling axis intercepts and the turning point with their coordinates. So example 13a is in turning point form. We've got a positive parabola, so it's often useful to identify the shape, whatever graph you're doing. This is a shape of a positive parabola, so we're going to look at something that looks like that. X plus 1 inside brackets is going to give us a translation of 1 unit to the left, and the minus 8 at the end is going to give us a translation of 8 units down. So we can start by marking in where the turning point is going to go. 1 unit left, 8 units down. Now this won't be perfectly to scale, but we'll try to make it as neat as we can. That turning point will happen at -1, -8. Of course, knowing that it's a positive parabola, it means it is going to come up and hit the x-axis twice, and there'll also be a y-intercept. So let's find those things. Starting with the y-intercept, let x equal 0, so we get y equals 2 times 0 plus 1 squared, take away 8. So y will equal 2 times 1 squared, take away 8. Y will equal 2 take 8, which is -6. So if we sort of try to keep our scale reasonably accurate, I guess -6 on the y-axis would look something like that. We've also got our x-intercepts. So x-intercept, let y equal 0, and then therefore solve for x. So we're going to get 0 equals 2 times x plus 1 all squared minus 8. Add the 8 over to the other side. 8 equals 2 times x plus 1 squared. Divide both sides by 2. We get 4 equals x plus 1 squared. Take the square root of both sides. We get plus or minus 2 equals x plus 1, which means that x will equal plus or minus 2 take away 1. So if it's positive 2 take away 1, we get x equals 1. If it's -2 take away 1, we get x equals -3. So we'll have an x-intercept at +1 and another one at -3. All right, so let's sketch this as neatly as we can. -3 might be sort of there on the x-axis, 1 might be there. Now, easier said than done, but always try to make sure your parabolas look symmetric on either side of the turning point, because they should be, and that they're curvy at the turning point and not like a sharp V shape. And of course, let's label the coordinates that we found. Y-intercept was -6. This x-intercept was 1, 0. That's -3, 0. Okay, second equation is given to us in polynomial form. So we've got a couple of different ways we could go. We could try to complete the square to get that in turning point form. Could even try to factorise it to get into factorised form if you wanted to. What we can do right away though is say that for the turning point, so the x coordinate of the turning point is going to be equal to -b over 2a, which in this question is -2 over 2 times 1, which is actually just going to be +2 over 2, so that equals 1. And of course, if we know the x-coordinate of the turning point, then we can get the y-coordinate of the turning point by subbing that value into the equation. So 1 squared take away 2 times 1, take away 15. That will equal 1, take away 2, so -1, take away 15, -16. So we know straight away that our turning point is at 1, -16. So like we did before, we can actually start our sketch by marking in the turning point, +1, -16, we're down here. Again, if you had a nice scale to work on, you could get that perfect, but for here we'll just do it a neat but somewhat rough sketch. We also know that because this term is positive, we're also going to get that positive U-shaped parabola here. So this graph will hit the y-axis, but also have, like the previous one, have 2 different x-intercepts. So if we're going to try to find, let's start by finding the y-intercept. Of course, we do that with letting x equal 0. And when it's in polynomial form, that's actually quite nice, because you're just going to get like 0 take away 0, take away 15. It's just the constant at the end will be the y-intercept. So you can sort of see that the y-intercept is only just higher than the turning point. And then we've got to figure out where is it going to hit the x-axis. So x-intercept, let y equal 0. And we will get, I'm trying to keep this in the camera shot, we will get 0 equals x squared, take away 2x, take away 15. We can solve this by factorising. Numbers that multiply to negative 15 but add to negative 2, well, 3 and 5 should work. We're going to need negative 5 and positive 3 to make that add up to negative 2. So therefore, x plus 3 equals 0, or x minus 5 equals 0, which means x equals negative 3 or x equals 5. So those are our x-intercepts. Let's put them on the graph. If that was 1, let's go, well, 5's maybe there, and negative 3. We're trying to keep this symmetric like it should be. Should have put a scale on the notes, I forgot. Oh, this one's looking a bit wonky. My first one wasn't too bad. This one's looking a little bit worse. So, labelling our key points. 1, negative 16. 0, negative 15. 5, 0. And negative 3, 0. And what you do notice here, and it was mentioned when we talked about factorised form up above, the x-coordinate of the turning point will always be halfway between the two x-intercepts. So if you had a situation where you actually found the x-intercepts first, x equals negative 3 and x equals positive 5, you would know that the turning point has to happen at x equals 1, because 1 is exactly halfway between negative 3 and 5. So that's another technique that you can use if you're sketching a graph like this.